RC circuit. We have a circuit with a 36 volt battery, 4 resistors, 1, 2, 3, 4, a switch, and a 5 microfarad capacitor. When the switch is closed, the capacitor is connected with the 12 ohm resistor in parallel. Case 1. Determine the electric current through the battery, determine the electric current in the 12 ohm resistor, and then determine the voltage drop across the 12 ohm resistor, all with the switch open. Case 2. The switch will be closed. After a long time, where t equals 10 times the time constant, determine the charge on the capacitor and the energy stored in the capacitor. Determine the electric current through the battery for case 1 where the switch is open. Since the switch is open, the capacitor is not part of the circuit. We want to find a total equivalent resistance. So the first step is look at what's perfectly in series, and that happens to be here, the 6 and the 12. We combine them and get 18, and there we go. There's the equivalent resistance for the 6 and 12. Now, do you see anything in this picture where you have a perfect parallel or a perfect series? Go to the next slide. We do have this setup here where these resistors are perfectly in parallel. R equivalent 1 we found on the previous slide is 18, and here's our 9 ohm resistor. We will now calculate 1 over R equivalent 2, just trying to keep track of our nomenclature. So that's 1 over 18 plus 1 over 9, and we get 1 R equivalent 2 is going to be 6 ohms. And it's always good to do a quick check. Is that 6 less than either one of those resistors? Yes, it is. I mean, it doesn't prove it's the right answer, but it would show it was the wrong answer if we came up with an equivalent resistance of like 12 ohms, for example. We redraw the picture, and what do we have here? Check on the next slide to make sure you got it right. The 2 resistors, the 3 ohm and R equivalent 2, the virtual resistance, are in series. So we find that R equivalent for the entire circuit now, right here. 6 plus 3 is 9. We can find the current, which will be the voltage over this R equivalent final, 36 volts over 9 ohms, and we get 4 amps. Now save these little pictures you have of each step, because depending on what else you're asked, you may use 1 or 2 of them. You just can't throw them away. Determine the electric current in the 12 ohm resistor. Okay, so let's sketch here. We've got 4 amps coming out of here. It goes through the 3 ohm resistor, still 4 amps, and then splits at this junction. We need to find the current through this one right here, through the equivalent resistance 1. Why? Well, what is that a replacement for? That's a replacement for the 6 ohm and the 12 ohm. They're in series, so whatever the current through the equivalent resistor is, it has to be the same through both the 6 and the 12 ohm resistor. So once we find the current there, we've answered this question. The voltage drop across this resistor and the equivalent resistance here are the same since they're in parallel. Also, those 2 currents have to add up to the 4 amps that came out of the battery and went through the 3 ohm resistor. So we show that the delta voltage across the 9 ohm is equal to the 1 across R equivalent 1. We substitute in IR equals IR, and we find that the current through the 9 ohm resistor equals twice the current through the equivalent resistance. And you could have just looked at that here, right? Because the 9 ohm is half the resistance of the equivalent one, so the current through it should be twice. Here's my other equation now. The 2 currents have to add up to 4. I substitute in the value for I through the 9 ohm resistor right here in terms of equivalent 1, and I get I through the equivalent resistance is 4/3 amps. And as we said earlier, once we found the current through the equivalent resistance, we know that the current through the 12 ohm resistor will be 4/3 amps. Determine the voltage drop across the 12 ohm resistor. We now have to go back to our original schematic because even though the current through R equivalent 1 is the exact same as the current going through both of these resistors, the voltage drop is different. They're in series. So the voltage across the 12 ohm resistor is equal to the current we found on the previous slide times its resistance. So that's 4/3 amps times 12 ohms, and we get a voltage drop of 16 ohms. Case 2. The switch is now closed. After a long time, t equals 10 time constants determine the charge on the capacitor. When the switch is first closed, all the current from this junction flows through the capacitor. Nothing flows through the 12 ohm resistor because there's zero resistance across the capacitor. However, after a long period of time, when the capacitor is fully charged, no more current flows. So the current is going to flow like this. The voltage it develops here will be the exact same as the voltage across the 12 ohm resistor when the capacitor was not in the circuit. Current will stop flowing at that point, right? Because whatever the voltage was supplied here by the battery, after it got cut down by these two resistors, and it goes to 0 here, that'll be the exact same voltage on the capacitor here, though of course this will be the plus end of the capacitor opposing the voltage coming from the battery. So what do we need to do? We need to find the voltage across this 12 ohm resistor after a long time, which is coincidentally the exact same voltage when this switch was open. We're now at equilibrium. The voltage drop across the 5 microfarad capacitor is the same as the voltage drop across the 12 ohm resistor, and that's just 16 volts. We found that earlier. So to find the capacitance, that's Q over V capacitance, but we're not finding that, we know that. We want to find the charge. We rearrange the letters, and we get the charge is equal to 5 times 10 to the minus 6 farads, that's what micro means, times the 16 volts that we found earlier, and we have 80 microcoulombs of charge on the capacitor when it is fully charged up. After a long time, determine the energy stored in the capacitor. Well, we've done all the hard work. Now we just have one more equation, 1/2 CV squared. We have the capacitance, we have the voltage drop across the capacitor, and we get the energy stored is 6.4 times 10 to the minus 4th joules.